All right, here we go. Benzoic acid has this structure, which you should know by now. COOH, carboxylic acid. It will form an equilibrium in aqueous solution. I'm writing this as H+, it's actually H3O+. And then the conjugate base here is called benzoate. Has resonance. Okay, so that is the basic chemistry. The benzoic acid can exist in this form, can exist in the deprotonated form right here. Ka is a measure of this equilibrium. You should know the format. This is the dissociated species here. I'll write it this way. That's pretty specific. This is the protonated species on the bottom. The brackets indicate molarities. Ka is something you can look up. For benzoic acid, 6.3 times 10 to the minus 5 is the value of the Ka. pKa is, you've seen pH, but pKa is the minus log of the Ka itself. And this you can calculate would be 4.2. If you just take the log of this value here, 6.3 times 10 to the minus 5, pKa is 4.2. So this is the pKa of benzoic acid. And this turns out to be a very useful number to know. Essentially, it's this. If pH, which you can control, is greater than pKa, then the deprotonated form dominates in the equilibrium. So in the specific case we're looking at here, if pH is greater than 4.2, it's mostly this. I guess I should write the if, huh? Mostly deprotonated. It's benzoate, mostly benzoate. And the opposite is true. If pH is less than pKa, then the proton is attached. So this is the significance of pKa. So this is useful because you can control the pH. You have acids and bases, you can add them, you can use a buffer, and you can say, I really want to control the pH. Alright, so that's pKa, and that's its meaning in terms of this equilibrium. Let's do some specific math now. So we have Ka equals H plus times the benzoate ion over benzoic acid, molarities. Alright, and now we know the value of that is 6.3 times 10 to the minus 5. And now let's say if pH is 3, which may be true in the soda. pH is low in the soda. So let's say H plus at pH 3 is 10 to the minus 3. And then I'm just going to express this as a ratio instead of thinking of that as individual numbers, because it is a ratio. And that's really what you care about. What fraction, what percentage is in each of these forms. Okay, so you should see that the ratio of the benzoate ion, based on this mathematics, to the benzoic acid is going to be 6.3 times 10 to the minus 2. Very simple algebra there. Which, if we reciprocal it, means that there for every benzoate, C6H5COO minus, comma, there are roughly 16 benzoic acid molecules. So it's 1 to 16 ratio. It's about 5% this and 95% that. So this is what's true in the soda. It's mostly benzoic acid. The ingredient label says potassium benzoate, but because the pH is low, it's mostly benzoic acid, 16 to 1 ratio. Now suppose pH is 8. We still have the same Ka value, but now H plus is going to be 10 to the minus 8 molar. Still have this ratio, C6H5COO minus, that's the benzoate, to the benzoic acid. So to make it pH 8, you can do that. You just add some base or you add a buffer and you make the pH be 8. You should see now the math is quite different, or the math is the same, but the conclusion is quite different. That the ratio now of the benzoate ion to the benzoic acid will equal 6.3 times 10 to the positive 3. And therefore, for every 1 benzoic acid now, there are 6,000 benzoate ions. We've completely shifted the equilibrium so that it now favors the benzoate. Let me write the conclusion. 6,300 benzoate ions for each benzoic acid molecule. Should make sense to you that we've changed the pH by 5 units. That's 10 to the 5th power. So the ratio has changed by 10 to the 5th power. So depending on which you want, do you want mostly benzoic acid? Do you want mostly benzoate? You just adjust the pH. You just adjust the pH and you have control over that ratio. Lastly, I'm ending with a famous equation. If we start with Ka equals this, we can rearrange this. I'm now using the generic X minus for some kind of weak acid. And if we take log of both sides, we can get to this sort of equation here. pKa equals pH minus log of this ratio here, X minus on the top, HX on the bottom. Whoa, having trouble writing that. And this can also be rearranged to say pH equals pKa. Let's do it this way, plus the log of the ratio of the X minus to the HX. So you can see if it's a 10 to 1 ratio between these two, then the pH will be 1 unit different than the pKa. And so you can use this ratio sometimes to control the pH, or you can use the pH to control this ratio right here. That's the lesson.